2.5 quintillion bytes of data are produced every day by humans, and 90% of that data was created in the last 2 years. And it's predicted that in 2025, each human will generate 463 exabytes of data a day. That is 463 followed by 18 zeros. But more than 80% of that data is unstructured and scattered. We need big data sets for important algorithms, like medical algorithms, because they need to be accurate. And more data, the more accuracy, generally. So let's say you had an algorithm that classified chest x-ray scans to see if a patient had pneumonia. Your algorithm needs to be extremely accurate. If not, your algorithm will give lots of false positives concerning people that do not need to be concerned, and leave a lot of patients untreated because they could live their whole life thinking they don't have pneumonia because your algorithm told them that they don't, but in reality, they do. Not to mention, pneumonia and a normal chest x-ray look very similar, so it's hard to distinguish. Even for an algorithm, it can take lots of images to finally see the differences between the two and do it consistently. So, we can get more data to make the algorithm better, because generally, more data means better accuracy. Some common data amplification methods are rotation, cropping, translating, flipping, blurring, shrinking, or scaling, and those can be easily done and automated with code. But that only makes so much data. You can only rotate an image so many times, you can only crop it different ways, you can only blur it so much, and some of those don't work for all applications. Rotation won't help with anything that has an orientation that matters and that consistently happens, like our pneumonia data set. They're never going to find a chest ray that is upside down. The people are always going to be standing in the same way. And flipping doesn't make sense if there's a lot of important features on a particular side. So let's say we have a data set with a chest pneumonia data set with 500 pneumonia images and 500 normal chest x-rays. We can start by looking at the augmentation methods that will work. Rotation, cropping, translating, flipping, blurring, shrinking, or scaling. And get rid of the ones that don't make sense for this use case. Rotation and flipping do not make sense in this case because the orientation matters and our features matter on each individual side. Then, using those methods, we can increase our data set, and our accuracy of our algorithm will generally increase with more data to train on. But what if we could further increase the data set and not have to do any little tricks where I rotate an image? What if we could actually generate more data, more pneumonia chest x-rays and more regular chest x-rays? Well, we can actually do this with GANs. Okay, what is this? How does it work? Generative Adversarial Networks, or GANs, was first created by Ian Goodfellow in 2014 and was called the most interesting idea in ML in the last 10 years by Yan Li Kun. GANs work by using two neural networks, a discriminator and a generator, that work against each other in an adversarial process, hence the name. We can think of the discriminator as a police and the generator as a counterfeit. The police gets two bills, one real, one fake, from the counterfeit, and decides which is more realistic with the percentage and gives those numbers back to the criminal, and the criminal then optimizes with a complex mathematical equation to get those numbers equal, so where his bills look indistinguishable from the real bills. Essentially, these two neural networks are fighting over a number, the discriminator loss. The generator wants the discriminator loss to be extremely high, so the discriminator doesn't know what images are real and which are fake. And the discriminator wants his loss to be extremely low, so he has to keep finding ways that the images are different. This process of the discriminator finding new problems with the discriminator's images forces the generator to get better at generating images that look indistinguishable from real data. Using GANs, we can increase our datasets, like the pneumonia dataset, by creating new data. But GANs are not just limited to making more data. GANs allow us to generate new data we haven't even seen before. But this is just a start for GANs. GANs open the door to many potential opportunities. We can compress files to make them smaller, to transport them with an autoencoder and decoder. Imagine a Google Meet where there's no buffering because each end has an autoencoder and decoder. The files are much smaller when you're sending them, and you decompress them when they go out. We can generate images just given text. Imagine you could get any image just typing in what you want. And you can make drawings look like realistic images. Imagine the next time you want a crazy good mock-up, you just draw it and the GAN generates the rest for you. And we can take generated buildings, parts, and optimize for certain aspects like weight, volume, and surface area with generative design. Hi, if you're interested in learning more, you can check out my GitHub where I show all the code for all the GANs and ML projects I've made. And you can check an article I made, and that will show you my results and maybe explain more in depth. Thank you.